Welcome to Spring LIB.
Hi, let us look at another problem. So now here we have a fixed axis at point A and we have a rod AB, and from that rod AB we have another rod hanging, which is rod BD, and then from point D we have another rod DE, and now DE is also fixed. So this is also fixed to rotate, so this is also fixed. Now what are the various lengths? So AB is 175 millimeters, BD is 200 millimeters. Then from point D to E, the vertical distance is 75 millimeters. And then from A to E, the distance is 200 millimeters. Sorry, 100 millimeters only. That means the total distance from D to E is 100 plus 175. That is 275 millimeters. Okay, so we are given these values, and then we are given that omega AB is 4 radians per second clockwise. So it's moving like this at a given instant. Then we are asked what is the velocity of angular velocity of rod BD and angular velocity of rod DE. Okay, to solve any of these kind of problems in this whole chapter, we have been following this rule: break the motion into translation and rotation. And since rods DE and AB are fixed, they are going to execute perfect rotational motions, so they will not have any translational component. But rod BD is going to execute a rigid body motion, so it will have both translation and rotation. So point B, it's part of a circle fixed axis at A, and since AB is moving with a clockwise velocity of 4 radians per second, the point B at this instant is going to have velocity pointing perpendicular to this radius vector AB, and it's going to point up because of this omega, and the value will be omega AB times the length AB. So this will be 4 radians per second times 175 millimeters. So how much will this be? So 4 5s are 20, 4 7s are 28 plus 2 30, then 4 1 is 4 plus 7 plus 3 is 7. So 700 millimeters per second. So this is 700 millimeters per second. And then if this is the translational velocity at point B, then at all points, even at point D, so let's call this Vt, at all points it's going to have the same velocity. So same translational velocity. So Vt at D also will be the same throughout this rod. That's the definition of rigid body. Translational velocity is same at all the points. Then it will have some sort of rotational velocity as well. Let us assume some omega, and then as I always keep emphasizing that even if you assume omega which is not in the correct direction, you will get a negative answer, which means negative of incorrect direction equals correct direction. So eventually we'll get the right answer. So let us assume everything to be clockwise. So this is clockwise. So let us assume this to be clockwise. If we assume this to be clockwise, then actually, yeah, so I always do that, but let me try to guess and see if I'm correct. So AB is going to move clockwise. So from the geometry, it seems to me that D is going to move to the left and B is going to move up. So this tells me that BD is actually going to probably move anti-clockwise and DE is going to move clockwise. So I'll assume like that, and then we'll see whether we get the correct answer. So let's assume omega BD to be like this, and we assume B to be fixed here. Motion is about point B. then what is the velocity of point D? So velocity of point D, if omega BD is like this, is going to point like this, perpendicular to the vector BD and pointing to the right because of this omega, assumed omega. So this velocity is going to be omega BD LBD. Now this is going to give you the net motion, and the net motion now at point B, since this is 0, this is translation velocity, so at point B is the same. As I said, it's moving in a circle, so it's constrained to, sorry, this circle. So it's constrained to move perpendicular to the radius vector AB. So it's going to point up, that's fine, and this is going to be 700 millimeters per second. This is the net velocity. And then at point D, since it's moving in a circle at this angle, a larger circle, let us see what D is going to do. So if D is moving left, I think the angular velocity here is also going to be angular velocity here is going to be clockwise. Yeah. So if this is clockwise, then the velocity at point D is going to point perpendicular like this to the circle, and the value will be omega dE times whatever the length of this rod is. So LDE this time. This will be LDE because we are looking at the circle of this radius. So omega dE LDE. This is the net motion at point D. Okay, now we have everything sorted out. T plus R equals net motion. So let's just break it down into components and equate the components. So let us figure out angles. So which angle is easiest to figure out? So let's look in this diagram. This angle is, I think, easiest to figure out because if this is a right angle triangle, then if this is theta, this is going to be theta. So the angle from rod D, angle of rod D from horizontal is going to be theta. If this is theta, then this is going to be perpendicular to the circle. So this is going to be 90 minus theta. So this is going to be theta. This is 90 minus theta. Okay. So now the vertical component, this component is going to be omega dE LdE cosine theta. And the horizontal component, I'm drawing it a bit too large because I just want to have space to write it down. This will be omega dE LdE sine theta. Okay, so I think we have got it correct because you can see that the direction wise we have got all the correct directions. So because this is pointing towards the right, the net velocity is to the right, and Vt is up, and the net velocity is also up. So we just equate. So Vt is the so at D vertical component, let me just write it down clearly. At D the vertical component gives us Vt equals omega dE LdE cosine theta. Now what is LdE cosine theta? So if you look here, cosine theta is base over hypotenuse, and hypotenuse is LdE. So it is base over, and the base is 275. So 275 over LdE. This is in millimeters. So then LdE cosine theta is 275 millimeters. So this tells us, so Vt is 700 millimeters per second equals omega dE. LdE is 275 millimeters. LdE cos theta is 275 millimeters. So omega dE. So you can see that now we have gotten a positive omega. If, for example, we have assumed an anti-clockwise motion, then this would point towards the left, and this would point towards the right. So we would have to say that, and the vertical component would actually point down. So in that case, we'll have to say that we'll get negative answer. So negative of clockwise is anti-clockwise, but here just by looking at the geometry, we assume certain omegas, and it turns out that we were correct in our assumption, so we are getting a positive number. But I'm just trying to make a point that even if you assume everything to be clockwise or everything to be anti-clockwise, or if you are not sure of your direction, you just assume something and start the problem. Once you equate the directions correctly and make sure that you are taking care of all the vertical and all the horizontal components, you will always end up with the correct answer. So here, so we have 700 millimeters over 275 millimeters. Millimeters will cancel. The final units are radians, which are dimensionless, per second. So 5 can divide both of them. In fact, I think both of them can be divided by 25. So 25 fours are 100, and 4 times 7 is, so this will be 28. And then this will be 25, 1 is 20, then 2, 5, then 25, 1. Yeah, so this is 28 over 11 radians per second. That is omega dE. So omega dE, let's divide this. So 11, let me just check. Is it 11 or so? 25, 1 is 25, then 2 and 5. So yeah, it is 11. Okay, so omega dE is 11, 2s are 22, then 6, and then 0, so 2.5. So you get 55, and then this will repeat. So let's just round it to 2.56 radians per second. And the direction was, assumed direction was clockwise. Sorry, yeah. So yeah, here I just said that it's the opposite of direction, but if you get a positive number, then your assumed direction is correct. If you get a negative number, then your assumed direction was opposite of the correct direction. So then your correct direction will be opposite. So if you get, for example, if we assume clockwise here, we would get a number which is minus 2.56 radians per second clockwise, which means 2.56 radians per second anti-clockwise. So you always get the right answer, no matter what direction you assume. So we got omega dE. Now this is from vertical component. So if we look at horizontal component now, so horizontal component tells us that omega BD times LBD, this has to give us omega DE LDE sine theta. Now similarly, if you look at this triangle again, the sine theta is going to be perpendicular over hypotenuse. Perpendicular is 75 millimeters, and hypotenuse is again LDE. So LDE sine theta, let me just write that this is perpendicular over hypotenuse. LDE over sine theta is 75 millimeters. So now let us substitute the values. So omega BD, LBD, I think it was 200. Yeah, it's 200. So omega BD times 200 millimeters equals omega DE, which is 2.56 radians per second, times LDE sine theta, which is 75 millimeters. 70 millimeters cancel. This is again positive number, so our assumed direction was correct. So omega BD, and our assumed direction was, I think it was anti-clockwise. Okay, so omega BD, then 25 can cancel both numbers, so 25 3, and then 25 8, I think. Yes, so this will become 2.56. Can it be divided by 8? Yes, it can. So 8 3, and so it will be 0.32. So omega BD is 0.32 radians per second times 3. So this is omega BD equals 0.96 radians per second, and the assumed direction was correct, and assumed direction was anti-clockwise. So anti-clockwise. So we figured out both omega BD and omega DE by equating horizontal and vertical component by breaking the motion into translation plus rotation. So most of these problems are basically geometry and trigonometry problems. The basic principles of physics are always the same.